Hi folks, so back again with another data analysis video and still looking at ANOVA, and in this video I'm going to demonstrate how to run a mixed design factorial ANOVA. Okay, so if you remember, a factorial design involves more than one independent variable. A mixed factorial design involves more than one independent variable and contains both independent groups or between subject variables and repeated measures within subject variables. So in this notebook, what I'll do is I'll analyze a data set that used the mixed factorial design with one repeated measures IV or independent variable that had 3 levels or conditions, and one independent groups independent variable or IV with 2 levels or conditions. So this study used a 2x3 mixed ANOVA design and it investigated the effectiveness of polygraph methods for detecting lies. So the repeated measures independent variable is called questions, and it recorded whether a participant told the truth, told a lie, or completed a control task in response to a series of questions asked by the researcher. And lying and telling the truth were self-reported by participants at the end of the data collection period. So the second independent variable, which was the independent groups factor, was called framing, and that assessed whether the framing of the effectiveness of the polygraph method for detecting lies influenced the results. And so for this independent variable, half of the participants were primed with a skeptical view of how effective the polygraph is before the study was conducted, and half were primed with a positive view, suggesting that the method was highly accurate and would definitely detect when people are lying. Okay, so the research assessed whether there were differences on the DV, on ADV, or dependent variable of mean arousal, measured by the participants' heart rate. So did their heart rate differ when they told a lie, when they told the truth, when they completed the control task? And in addition to that, it assessed whether mean arousal differed between the levels of the framing condition. So was arousal different when people had a positive or a skeptical view of the effectiveness of this as a polygraph, a lie detector method? So independent variable 1 was questions, 3 levels, lie, truth, colored squares. That's the repeat measures variable. Independent variable 2 was framing, called framing, 2 levels, positive or skeptical framing of the effectiveness of this particular test, essentially. And that was the independent groups measure. And the DV, the dependent variable, was kind of mean arousal as measured by their participants' heart rate. So what I'll do is I'll conduct a mixed ANOVA using this particular data set, including doing some tests of assumptions, run the ANOVA model, and then any post hoc or simple effects tests that might be required. Okay, so to start with, I'm going to import some key software libraries. I'm going to import pandas, numpy, scipy, matplotlib, and seaborn, because we'll ask for an interaction plot, and pingouin. I'm going to use pingouin to run the analyses for this particular model. Okay, and the data set, I've got it saved as a CSV on my laptop. It's called HR polygraph long.csv. I'm going to import it using the pandas pd.read_csv method, and I'm going to call it HR_df, so heart rate data frame essentially. Let's look at the header for this. So I've already kind of wrangled this, so it's in a long and thin format. So mean arousal is our DV, our independent variables are framing and questions. If we look at the info, you can see that we've got 240 participants. There doesn't seem to be any missing data. Interestingly, so questions is saved as an object, which is correct. It's a string variable and it contains 3 categories. Arousal is saved as a floating point number, which is correct. It's kind of a decimal. It's kind of a decimal numeric representation of heart rate recording. Framing, though, is shown as also as an integer, and remember this is a categorical object, positive or skeptical. So there's a tiny little bit of wrangling that we need to do here first, and that'd be good to basically give category labels to the framing variable. So it's currently being given a numerical code of 1 for skeptical and 2 for the positive group. It'd be useful to have this saved as a categorical object with the appropriate labels. and that will help us with interpreting the output later on. It'll also avoid confusion as to which group was coded as 1 and which was coded as 2 when we're kind of look at if we're looking at post-hoc or simple effects comparisons. So the easiest way for me to deal with this is to create a new variable that maps those integer values 1 and 2 in the framing variable to labels using the series map method. So I've demonstrated this a few times previously. So all I'm going to do is create a list called A, and that's going to contain the integers 1 and 2. Create a list called B, which is going to contain the labels skeptical and positive. And I'm going to create a new variable and append it to our heart rate data frame, calling framing underscore cat, so framing categorical. And that's going to take the data in the framing in the framing variable as it currently is, and I'm going to use the dot map, the series map method, pass it a dictionary, and tell it to zip these lists A and B together. I've demonstrated that in previous videos, and if we look at the header now, we've now got this new variable appended to the data set, which shows skeptical where there's a 1 and positive where there's a 2. If we look at the info, that should also now be saved. It should have, Pandas has correctly identified that that is an object, which is kind of useful to have it in that format, I think. So the data's sorted. Let's now do the analysis. So firstly, we're going to do some tests of assumptions. We've got both an independent groups and a repeated measures IV here. So if we're going to do a couple of quick tests of assumptions, we might want to conduct a Levene's test to test for homogeneity variance for the independent groups variable, and also Mauchly's test as sphericity for the within subjects to be the repeated measures variable. Okay, so I'm going to use pingouin to do both these tests. So for Levene's test for homogeneity of variance, I'm going to use the pg.homoscedasticity method. I'm passing it our HR data frame. The DV is obviously arousal. The group variable is our framing categorical variable. That's positive and skeptical. I'm asking it to use the mean as the center. So if I run that, and then the sphericity test as well. I'm going to use to conduct Mauchly's test of sphericity. I'm using the pg.sphericity method. And you can see the parameters, the arguments I've passed in are slightly different. The data is still the same. It's the heart rate data frame. The DV is arousal. This time we've got to specify our subject ID. We need our participant ID number essentially to account for the fact that participants are contributing more than one data point. And then we're passing in our within subjects variable, which is the questions variable, and I've passed that in brackets as a list. Okay, so let's run that. And for the Levene's test, we get kind of a nice HTML output, pandas pandas table essentially. For sphericity, less so. We get the results we need. So for Levene's test, we've got a test statistic of 5.61, a p-value of 0.02, and it tells us it's false that we can assume equal variances. So we've kind of violated the assumption of homogeneity variance with this data set. So we can't assume equal variances, which is problematic to some degree. For sphericity as well, it tells us sphericity, the assumption of sphericity, can we assume sphericity? False. It gives us Mauchly's omega 0.88, chi-square is 9.82, 2 degrees of freedom, and a p-value of 0.007, so a statistically significant Mauchly's test as well. This is somewhat problematic, as we can see above. We can't assume equal variances for the independent groups factor, nor can we assume sphericity for the repeat measures factor. And here you can see this is how you would essentially, how you might formally report those results for the Levene's test. It's an F test, so we do F and then in parentheses the degrees of freedom, 1 and 78. The F value is 5.61, P is 0.02. And then for Mauchly's test, I've said this previously, it gives you this omega W value 0.88, gives you a chi-square value. You can report all three of those, I suppose. I don't see a great issue with that. So what I'll do here, we've kind of got an issue to start with, that we haven't met the assumptions necessarily of sphericity and homogeneity. But I'll run the mixed design ANOVA using the pingouin mixed ANOVA method, and we can then use an adjusted p-value now where necessary to interpret the significance of any results that we might what we're going to find here is we get significant interaction. So that's the main thing we'll be interested in, and making sure we use a kind of robust adjustment. Okay, so to conduct the 2x3 mixed ANOVA, what I'm going to do is create a new object called mixed_res, so mixed model results essentially, and I'm going to use the pingouin pg.mixed_ANOVA method. So it has a specific method within the Pingouin software library, which is a great stats software library for conducting mixed design factorial ANOVA. And we've got to pass a number of arguments to it, a number of parameters. So the data is our HR data frame. The DV is obviously still arousal, mean arousal. Our within subject factor is the questions variable. Our subject is the ID variable, so we have to include that obviously, so we know which data points on the within subject factor came from which participant. And our between subject factor is the framing categorical variable. Okay, so to know what parameters are required for this kind of method, if you look on the Pingouin webpage, you can see it tells you the documentation for it, tells you kind of what things you need to include. So if I run that and call the mixed res object, you can see it gives us a kind of an F table, an output of the ANOVA results. So gives us a result for the main effect of framing, the main effect of questions, and the interaction, which it labels interaction. And it's for the sphericity, for questions within subject factors, it's allowed us to use a corrected p-value. It hasn't for the other two, but that's not too much of a problem here. So we can see from these above that these results here, we have a significant main effect of framing when using the uncorrected p-value. So it's just about 0.05 if we round that to 2 decimal places. Yeah. A significant main effect of questions using the greenhouse geyser corrected p-value. So if we round that to 2, that's 0.05. And we'll say that's significant. So we've got significant main effects, but we've also have a highly significant interaction between framing and questions. And we're having to use the uncorrected p-value for the interaction, but it's so small, it's 0.00006. So although we've not got an adjusted p-value for the interaction term here, it's an extremely small p-value, and it suggests that it will still be significant if we conducted a robust test on this data set. So as the interaction is significant, this indicates that the main effects, although they're significant, are not likely to be consistent. So the next step for us is to conduct tests of simple effects and interpret this significant interaction. All right, so a good place to start when we're kind of looking at interactions and simple effects is to create an interaction plot to visualize the differences between groups using the Seaborn point plot method. So I'm using SNS.pointplot. The data is our HR data frame. The X variable is questions. So remember, I've said previously, when you're creating these types of interaction plots for ANOVA, Factorial ANOVA, whichever of your independent variables has more levels or groups or conditions, put that on the x-axis, and then whichever has fewer, represent that using the different colors. So the hue argument in this case for Seaborn, using different colored lines essentially. So our x variable is going to be questions, got 3 levels: lie, truth, control. Our y variable is going to be arousal. That's obviously our scale DV variable. The hue, or the different colors of the lines we're going to plot, is going to be our framing, so positive and skeptical. I'm asking it to use circles and squares as different markers, and there are a number of different color palettes. I've kind of just stuck with colorblind. I think is probably the default. But if we run that, I mean, I could have asked for a bigger plot so it looked a bit nicer, but this is all we need essentially. So you can see here we've definitely got an interaction going on. We've got what will be referred to as a disorderly interaction, because the lines are actually crossing, so we're getting kind of seem to be getting different effects at different levels for one independent variable at different levels at the other. So it looks here like in the lie condition there's a significant difference between skeptical and positive. These two group means are very different. The error bars don't overlap, with arousal being much higher in the positive condition when people lied. Based on the priming, that might make sense because they might be more nervous that they might get found out, and that's been a consequence of that. But there doesn't seem to be any significant difference in the truth or control conditions. Okay, so some interesting results, and this is why kind of although we've got we had these significant main effects, if we just considered framing or if we just considered questions, they're not consistent. So the main thing we need to do is essentially investigate further what is going on with the interaction. So what I'm going to do is I'm going to create some new objects. So we've got one group for each of these data points, the 6 kind of groups that we're going to compare really. And what I'm going to do is I'm going to create a new object, say skeptical lie, and I'm going to use the .load method. And what I'm telling it to do is take the framing category, and wherever it's the string says skeptical, and also take the questions variable, and wherever it says lie, extract those observations, those data points, and here what we're doing is basically extracting the mean arousal score. So we're basically creating an object here that just contains the skeptical lie arousal scores, essentially. Same as skeptical truth, an object that just contains the skeptical truth arousal scores. So that first group would be this mean, second group this mean, type of thing, or would be the data points that contribute to this mean and this mean. Let me run that, and then what I'm going to do underneath, you've kind of seen me do this a number of times now. I'm just going to use print statements and f strings, and we're going to print out we're going to take each of these objects, ask for the mean for each of those objects. So we've extracted the data points by group. We're going to then work out the mean of the group and just round them to 2 decimal places and print them out like this. So there you go. That's all we've done there essentially. So you can see skeptical and lie has a mean of 69.28. So that would be this data point here. Positive and lie has a mean of 88.38. That would be this data point here, which kind of makes sense if you look at the values on the y-axis. All right, so we've got an interaction plot, we've got some descriptives, we've got the mean group scores. So inspection of that interaction plot indicates there's a significant difference in arousal between the skeptical and positive framing condition when participants lie, with those given a positive framing of how effective the technique is, experiencing higher arousal. So however, there doesn't seem to be a significant difference between frame conditions at truth and control levels. So when considering the skeptical group, the blue line, just in isolation, there also does not appear to be a significant difference in arousal between lie, truth, and control. So if we scroll back up, you see what I mean by that. This blue line here, there's some difference between this point and this point, but there's a lot of overlap, and this is almost a flat line, this blue line, and if we look at the positive only group, so just that orange line, we see that arousal seems to be significantly higher for lie and when compared to the other two. And further, the truth and control condition do not seem to differ significantly. So if we look at that orange line, so with this seems to be higher than these two other positive points, and these two don't seem to be different. Okay, so tests of simple effects in the forms of pairwise comparisons can be conducted to that's our intuition just looking at the plot, But we can do these tests of simple effects to assess which differences between groups are actually statistically significant. Okay, so I'm going to run pairwise comparisons using the penguin pairwise test method. Okay, so this is how we're going to tease apart the simple effects here. So I'm going to use a Bonferroni adjustment to make the test stricter, because we did have a lack of homogeneity variance for the sphericity and sphericity in this data set. And also we're doing multiple comparisons, so we need to do that. So let me run this. So what I'm doing here is I'm creating an object called simple F, so simple effects, using pairwise tests. We're using the HR data. Our DV is arousal, our between subjects, the framing category, within subject questions, subject identifier is the ID variable, so we know which participant contributed which value to the repeat measures variable questions, and we're going to use a Bonferroni adjustment. Let's run this, and what we get here is a nice table of output with a load of comparisons. So what's important, if you don't know your way around this, it could be a little bit tricky and misleading, but note that this output only gives us 3 of our simple effects comparisons that we wish to make. So we ignore the first 4 rows, this 0, 1, 2, 3, because these are basically our main effects. So this is just looking at the questions variable, ignoring framing, and comparing control to lie, control to truth, lie to truth. And then this is just looking at framing, ignoring questions, and comparing positive to skeptical. Okay, the rows 4, 5, and 6 here are the ones we're interested in. So what we can see here is if we look at these, we can see that pairwise comparisons have been conducted, holding each level of questions constant and comparing the framing conditions. So here, if we look, each level, this row here is if we just take the control condition, comparing positive with skeptical. And this one here, if we just take the lie condition, comparing positive with skeptical. If we just take the truth condition, comparing positive with skeptical. So that's the equivalent if we look at our interaction plots. That's the equivalent of if we just look at lie, compare this data point, this group mean with this group mean. If we just look at truth, compare this one with this one. If we just look at control, compare these two kind of slightly overlapping. Difficult to see. All right, so what does this tell us essentially? What we can see is that the positive and skeptical group means are not statistically different in the control condition. So if we look at control, positive and skeptical, we get a t-value of negative 0.07 and a corrected p-value of about 1. So it's not there's no significant difference between those two. It's not going to be exactly 1, but yeah. The positive and skeptical group means are significantly different in the lie condition and are not significantly different in the truth condition. So we can see that if we look at lie, we get a t-value of 5.00 and p is exactly equal to 0.00001. Okay, if we use the corrected Bonferroni adjusted. So if we look at the t, the truth condition, same sort of thing, positive and skeptical, negative 1.66 or 1.66 if we just report that, and 0.30 is our p-value. So I've given an indication here. So to report these, this is how you might formally report these results. So for control, we've got positive condition as a mean of 73.88, compared to the skeptical condition, a mean of 74.15. There wasn't a significant difference, and this t, degrees of freedom of 78 is equal to 0.07, p is equal to 1. Okay, so that's that first row there. Likewise, to report the means, I've just extracted them from our printout above there. So it's clear, all right, so someone looking at those can go, all right, so There was a significant difference between in the lie condition between positive and skeptical, and you can see that straight away. Oh yeah, positive had a higher mean than skeptical. Okay. So there are actually further tests we would like to run where we'd hold framing constant and compare the 3 questions conditions. Okay, so this has only conducted some of our simple effects tests for us by running it this way. So in order to do this, what we're gonna do is run this again, but we're going to change the syntax slightly and specify a parameter that says within underscore first equals false. Okay, so if you look at this particular cell here, what you can see is we're using a Bonferroni adjustment again. It's pretty much the same, but we're asking within underscore first. We're setting that to false. We've added this extra parameter, and what that will give us is, rather than here it's given us it's held questions constant and compared framing, it will do the opposite. It will hold framing constant and compare the 3 levels of questions, which will give us a more complete set of simple effects. So we've only got, in that first table, we've only got a partial set of simple effects. So hopefully you can see here the difference. So again, we can ignore these first 4 lines, 0, 1, 2, and 3, because they are the main effects. And the ones we're interested in here, these 3 lines, 4, 5, and 6, we're holding the positive framing condition constant. 7, 8, and 9, we're holding the skeptical framing condition constant. And here we're holding positive constant, we're comparing control with lie, positive constant comparing control with truth, positive constant comparing lie with truth. Okay, so we're looking to see if we've got significant differences. So in this second output table, we see framing's being used as the variable that's been held constant, and each level of the questions are being compared. Okay, so what the results show is, in the positive condition, control and lie have significantly different mean arousal, and lie and truth have significantly different mean arousal. However, control and truth do not have significantly different mean arousal. When we look at the skeptical condition in isolation, we can see that none of the question levels are significantly different from each other. So let's look at what that means on the interaction plot. So what if we just look at the positive condition and compare the 3 group means? What we're seeing is, just look at the orange line, we're seeing lie is significantly different to truth. So, and like with mean arousal being significantly higher in the lie condition, lie is significantly different to the control condition, with arousal being significantly higher in the lie condition. That truth and the control condition don't significantly different. We knew that just by visualizing this, I think, because of the large overlap. But then if we just look at the blue line and we compare lie to truth, lie to control, truth to control, none of these data points are significantly different. And we could have guessed that as well. We kind of, our initial thoughts were that was the way the results were going. Okay, so the results confirm what we could see in that interaction plot, as the skeptical blue line was almost completely flat. So the results of these comparisons are kind of summarized below. So this is, if we look at the positive condition, we compare control to lie, positive condition, control to truth. I'm not going to read those out, but you can see I've just kind of reported each of the t-values, the t-statistics and the p-values, and reported each of the means for those groups. Okay, again, the means, I've just read them off this table, this output here that we obtained. Right, so overall, these results indicate that framing can influence the results of a lie detector test, and only participants who've been given a positive framing of how effective it is as a technique are likely to experience higher arousal when telling lies. However, if participants are given a skeptical framing and led to believe the method isn't effective, they're likely to experience lower or normal levels of arousal. That normal levels of arousal when they lie that are no different really to when they tell the truth. Okay, so what these results indicate is that if someone who administrates or administers a lie detector test could influence the results based on the belief they can induce in the participant. So we wouldn't. It seems to indicate that this kind of method isn't a reliable technique for detecting lies. It strongly indicates that. Okay, so hopefully this was useful. So that was a mixed design ANOVA. So we had two independent variables. One was a repeat measures independent variable, which had 3 levels: lie, truth, colored squares. So participants took part in every level of that independent variable. The other was a between subjects independent variable. So only half the participants received a positive framing. The other half received a skeptical framing before they took the lie detector test. And the DV was kind of their mean arousal when they lied, when they told the truth, when they did this control task, essentially. And the results, kind of probably visually best summarized by this, is like when people believed that the method was effective, then they experienced higher arousal when they lied compared to if they had a skeptical view of the method for detecting lies. But there were no significant differences because across the other groups. Okay, so that hopefully that was useful. So what we did was conducted a mixed factor ANOVA, a 2x3 ANOVA. We found we had a significant interaction. We found we had significant main effects, but they weren't particularly interesting because of the significant interaction. So the thing to do was to look at the significant interaction to interpret what was happening. All right, so I am going to make one more video about ANOVA, and then I'm going to stop making ANOVA videos because I think this might be video number 12 and kind of quite bored of it now, so we'll go on to something else. So the next video, what I'll do is I think I'll cover some of the assumption tests for ANOVA in a bit more detail. I've kind of done it in a very ad hoc way over the previous few videos. So to finish off, I'll quickly cover some tests of assumptions that are relevant for ANOVA in a bit more detail. And then after that, I'll start making some videos about regression, simple regression, simple linear regression, and how to conduct multiple regression. Okay, hopefully this was useful. Thank you for listening.